I think astronomers have sort of lost their way. I guess all my listeners already know that. They ignore chemistry that's happening inside of stars as they evolve, and inside of, stars as they evolve, or you want to call them planets as they evolve. Because they look at Jupiter, they look at Saturn, they look at Neptune and Uranus and the Earth, and they say, well, it must have formed at this size and the same chemical configuration that it is now, and its iron nickel core is just this thing that's just sunk there because the iron nickel is heavy. There's no thought into, hey, maybe the iron and nickel is leftover catalyst. And what a catalyst is in chemistry terms is something that speeds up or makes easier chemical reactions, but is not consumed in the chemical reaction. We all remember in chemistry class when you take two chemicals together and you mix them, they can become a different chemical altogether. Or you take two chemicals and you mix them and they split, they interact with each other and they become two different types of chemicals. You have double replacement and single replacement reactions, all that stuff. But basically, for my listeners, I don't know if they remember the chemistry back in high school, but a catalyst is something that's unconsumed. So say, for instance, you have two chemicals. I'll use my AirPods as an example. You have two chemicals. A catalyst is platinum or osmium or iridium or iron and nickel in this case. And say, for instance, you have a thick atmosphere like Jupiter. That iron and nickel that Jupiter receives comes from outer space in the form of meteors, meteorites, and that kind of stuff. So it enters in the atmosphere, it combines with those two chemicals, the catalyst does, and then that makes it easier for these to clump together. Because if they didn't, they would have to have a lot more energy to do so. And here's a little graph showing it. This is the potential energy. And this little line right here is the amount of energy needed. A lot of energy is needed to create that new chemical on this side. So you have two reactants that are not together. You have a catalyst down here. And what happens is when you introduce catalyst to these two chemicals, one can combine and it goes through a smaller energy barrier, and then it combines the other two to the catalyst itself. The catalyst sticks to them, I guess, and then it takes those three individual parts and it connects it into one, and the catalyst just goes back, is recycled through the system, and it repeats the process again. So you have unconsumed catalysts being able to make a very wide range of chemicals that exist inside the atmospheres of evolving stars. And being that the catalyst is unconsumed, after all the chemistry has taken place, after all the evolution has occurred, after the star has completely cooled down, that remaining catalyst will remain in the center. It'll start sinking into the center because it's done all the chemistry it can, and it's just heavy, so the star can't get rid of it. So it starts sinking into the center of the star. This is why we have the oldest stars with iron and nickel alloy cores, of course, with trace amounts of iridium, trace amounts of osmium, trace amounts of gallium, which were all essentially catalysts in their own right at different temperatures and pressures. Of course, I believe the iron and nickel are catalysts at extremely high temperatures and pressures, which is why they're still unconsumed and why they can combine into the center of the star as the star has evolved. So they're unconsumed catalysts, meaning they didn't combine with other elements as they went down. Of course, you have things like iron oxide, and you have iron banded minerals, but that iron came around after the fact. So there's probably low pressure and low temperature reactions that took place with that, or the iron probably connected to the oxygen in the more highly evolved stars, and then it deposited in the center. But when the iron is, I guess, in its atomic state, it acts as an extremely good catalyst, and then it combines with itself and nickel in large amounts and sinks to the interior of the star. And this process is occurring inside of Jupiter, Saturn, Neptune, and Uranus. These are more evolved than these, which means they have more material to catalyze, and they didn't have enough time to collect as much iron and nickel as Neptune and Uranus have But of course, Neptune and Uranus, iron and nickel cores, it's not on here. It doesn't say that they have iron and nickel cores, but we know they do. They're forming in their interiors. But what happens is those iron nickel meteorites enter in, they mix with the high atmosphere, combine a lot of chemicals together, make things extremely complex, which means the chemistry of Uranus Neptune is much more complex than Saturn and Jupiter. Of course, if you continue on this process and you collect even more catalytic material to make different chemicals with, and spur the creation of the organic portion of a star's evolution, which, when it takes all that carbon and it combines it in different arrangements too. And it'll start forming at the top of Earth. When Earth was an ocean world stage, so between Neptune and Earth is where the oceans were, but still, that was when the Earth, that remaining iron nickel material had already collected in huge amounts in the center, and all the chemistry of the preceding evolutionary periods has already been formed. So look at this as a time scale. You have the very, very, very center is the oldest portion, because that's the portion that formed first. And as you move outwards, the age of the material decreases significantly, which means the crust of the Earth is the youngest portion, which is made of rocks and minerals and stuff like that. And then the deeper you go, the older you go. So that's in line with the geological principle of superposition as well. For those people that, about tree rings, the oldest ring on a tree is the very center of the ring. So look at that as the interior of a highly evolved star. The very center of the star is where that remaining iron nickel catalyst had first began forming. And as you move outwards, the younger and younger the material gets. But for this talk, I just needed to bring up another point. The amount of life that's on Earth right now on its surface, and coupled with the size of the iron nickel core, that huge iron nickel core signals that there was a hell of a lot of chemistry happening on the Earth much, much earlier in the Earth's history. Which means if we find stars that have similar sized iron nickel cores, such as Mars, Venus, and Mercury, we know 100% for certain that the same amount of chemistry was occurring on Mars, Venus, and Mercury. Now, they are different sizes now, but they weren't always like that. Remember, Earth, I say between 4.5 and 10 billion years old. Venus, go to Mars. Mars is around 20 to 30 billion years old, but also is on a lower transformation curve. And Venus is around 450 billion to 700 billion years old. And Mercury I have as 7 to 32 trillion years old. So there's a hell of a lot of time for all this mantle material to be eroded away. But it kept its iron nickel core that size that it is, because that signals that it's the remains of a very, 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 very old star. And that's the only way you could have formed an iron nickel core that huge. And astronomers are still confused by that. They don't know why Mercury's core is so comparatively huge compared to its actual size. Well, it's directly evidenced by the size of its core. And the only way we can understand that is through better theory. And the better theory is the realization that Mercury is the remains of a very, 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 very old star. It's way, way the heck down here. I think it's like down here. I remember something like around this area. But I had written a paper about it, and the reason why I want to talk about it in particular is because this paper only had like 11 views, 11 unique IP downloads, so people were just ignoring it. But it's very essential to understand that the amount of chemistry that's involved during stellar evolution is evidenced by the amount of iron nickel, the size of the iron nickel cores of these highly evolved stars, which is the remaining catalyst that signals how much chemistry was occurring in much, much younger stages when that star had a much, much thicker atmosphere. Of course, this goes directly against the dogma where they say, something like the Earth formed as it is in its current size. And then they say, well, it was the iron catastrophe where the iron just sunk there magically without any reason. And all the material that's in front of it just moved out of the way for no reason. Of course, that's a very poor hypothesis, based on a very poor assumption, which is based off another very poor assumption that's snowballed since like the early 1700s. Now that we have all the information coming from Kepler and the tests and all that, we can, just fix all this stuff and go back to real science again. All right, I'll link this to the bottom of the page. Of course, if you want to look up catalyst reactions, just type it in Google. Type in catalytic reactions. It lowers the amount of energy. So this is a high amount of energy, and this is low amount of energy. A catalyst makes sure that those reactions can happen with much, much lower amounts of energy required to overcome that barrier. All right, guys, that's it. Hi, Celeste.